Dear students, we continue physics for scientists and engineer, chapter number 23. So example number 8. In the previous lesson we discussed the if the charges are distributed continuously on the any surface, so we have to find the total potential. So total potential can only be found by using this formula. V is equal to 1 over 4 pi epsilon naught 1 over r integral dq. We just integrate the total charge to get the total potential. Okay. So example 8, the potential due to a ring of charge. Suppose we have a ring of charge and the potential is distributed continuously on this ring. Okay, now let me draw the diagram first. So for example, if we have a ring of charge, this is a ring of charge, and the ring, the charges are distributed continuously over the surface. This is continuous distribution. What is mean by continuous distribution? The charge has the same distance between them and charges has the same magnitude, mean the continuous. Okay, now we need to find the potential at point P, at any point P away from this, away at this point P is at the distance x. This point P is at the distance x from the center of this ring, okay, so that the radius of this ring is represented by capital R, and we need to find the potential at point P due to this ring of charge. Okay, so as the charges are distributed continuously on this surface, so for the continuous charge distribution we divide this surface into very small length elements. Each length element has small charge dq, and we need to find the total potential. So in order to find the total potential, we use the formula V is equal to 1 over 4 pi epsilon naught integral dq over r, and we just integrate this term, integral term 1 over 4 pi epsilon naught 1 over r and integral dq. Because we know that the charge is distributed continuously, we just integrate for the whole surface, so the total charge integration of dq is simple q. So V is equal to 1 over 4 pi epsilon naught 1 over, and dq, integration of dq is simple q. And what is distance r? So r is the distance from the small q, small element of charge q, to the point P. This distance is r. So if we use the right angle triangle, for example, this is r, this is x, and this is small r. So the small r is basically, you can see that this is the right angle triangle. This small r is, we use Pythagoras theorem. So the Pythagoras theorem says that hypotenuse square is equal to base square plus perpendicular square. So hypotenuse is r square is equal to base is x square plus perpendicular is r square, capital R. So r is under root x square plus r square. So this term is x square plus r square square root. Okay, now we can replace r with the under root of x square plus r square and q. So this is the charge. So this is the potential at point P. Okay, now we use a simple case. For example, if we say that this point P is very far away, this point P is very far away at the infinite distance. So if this point P mean the x distance is at the infinite, so if x is greater than r, so it means r becomes very close, very zero. When we see at the very high distance, this ring looks like a single point, mean the radius of its radius become zero, because when we see it from a very large distance, so we can see it as a single point, mean its radius becomes zero. Now we just put this r in zero in this above equation. Suppose this is, for example, equation star. We just put r0 in this above equation and we are left with the another result, astonishing result, that is, so I write here on the left side. So V is equal to 1 over 4 pi epsilon naught q divided by x square under root plus 0 square. So this square and root cancel, so we are left with the 1 over 4 pi epsilon naught q over x. So this is the same result that the potential due to a single point charge. Okay, thank you.